Hello and welcome to Global Azure 2023 and welcome to my session building a serverless multiplayer game. My name is Sklenitzka. I'm the co-founder of softaware in Asten near Linz, where I work as a solution architect. We're an individual software developer and we use Azure in one way or another in, I'd say, about 90% of our projects. Today, I want to show you a special mix of technologies, of Azure technologies that we can use to build a serverless multiplayer game. And without further ado, I'd like to show you what we're going to build in this session so that you know where we're headed. I've got two browser windows open here, two different browsers. Of course, they're running both on my machine here, but you can imagine that you can play with anyone on the world using just your browser. This is running in Azure, as you see here, and yeah, it's a simple tic-tac-toe game. We're going to implement this in the next 43 minutes, but yeah, you can use the same techniques to build more complex games, of course, or actually you can build anything using the same techniques. You don't need to build games. I just thought it would be fun to build a game in this session here. So two browser windows and I can play tic-tac-toe. And as you see, once I click in one window, immediately the other window is updated. So we've got a real-time communication here. And yeah, now I'm going to switch back to my slides and I'm going to show you the technologies we can use to build this sample. But first, I have to talk about the serverless part of the title of the session. Because what is serverless? If you ask this question to 10 developers, then you probably get 12 different answers because everyone has a little bit of different understanding what actually is meant by serverless. For this session, the context is that, of course, we're going to need a server where our app is running, but I don't really care about it. I just want to write my code. I'm a developer. I want to write my code, push it to the repository, push it to Azure, and it should run there. But I don't really want to have to think about how many servers do I need to run this? Does it scale? How much CPU do I need? How much memory do I need? I'm not really interested in that. I want Azure to take care of that. I want to use auto-scaling so that when there are a lot of users who play this game simultaneously, then it's okay that we maybe have multiple instances of our resources running so that we can handle the load. But for example, during the nighttime when no one is actually playing, I don't want to use resources in Azure and I don't want to pay for them. So this is also an important point. I want to make use of pay-per-use. I only want to pay for the resources I actually use. And yeah, my app should take care of this whole scaling. So this is the context, what I mean by serverless for this session. Okay, so let's start with the different technologies that we're going to use to build this. The first one is static web apps, and that's used for global hosting of static content. So if you think about a web app, it's made up of different files that need to be served to the users, usually HTML files, JavaScript files, CSS files. In our case, we're using Blazor, so we're going to download some DLLs. But we always have some files that need to be delivered to the client in order to run the app. And we can use static web apps for this delivery and for the hosting of the files. And for the global part, this is something we get for free with static web apps. So we just push our code to the repository, it gets built, pushed to Azure, and Azure takes care of distributing our files to various data centers around the world. And whenever a user wants to access our app, he can just connect to the nearest data center and get the file from there. And yeah, that's pretty fast. We have very low latency because of that, but we don't need to implement that ourselves. Static web apps does that for us. We can use serverless APIs in combination with these static web apps. We're going to use Azure Functions. I'm going to talk about that in a minute. And another important point about static web apps is that they come with pre-configured CI/CD workflows. So it's very easy to get up and running in Azure. You just push your code in our example, it's going to be GitHub. You can also use Azure DevOps, for example. You just push your code to the repository, and there are already workflows available that automatically figure out what kind of web app you're using. So is it Blazor, like in our case? Is it Angular? Is it React? Or whatever framework you're using. It builds your app and it deploys it to Azure. And yeah, so it's very, very easy to get started with these static web apps. I already mentioned Azure Functions. So we're going to use Azure Functions for implementing our backend logic. And the main idea of Azure Functions is that I have some small piece of code that I want to run in the cloud in Azure. So you don't deploy a whole application, a whole monolith, but you have these individual small functions, small pieces of code that you want to run, and you want to run them when certain conditions are met. So it's an event-driven architecture. These functions are going to be executed when different triggers are activated. So for example, you can have timer-based functions. You want to run an import once every night at 2 a.m., then you can use a timer-based function. You can write functions that handle incoming HTTP requests for building REST APIs. You can write functions that are triggered by messages in a service bus queue, for example. That's useful for decoupling different systems. And there are many more different triggers available that we can use. But yeah, overall, it's an event-driven architecture. We have some code that we want to run when some event is activated. Here's a small code sample how such an Azure function looks like in code. I've used C# here, but you can use different programming languages. And in this case, it's more or less a normal C# function. It has this function attribute applied to it, where we also apply a name for the function, and we have some kind of trigger. So I just talked about triggers. In this case, we want this function to be triggered by an HTTP request. So we use this HTTP trigger attribute. We can specify some parameters like which HTTP method should be used, which route should this function be available at. And then we get the HTTP request data as input parameter into our function. We can also use some placeholders in the route, for example, and also inject these as parameters to our function then. And one other interesting thing about these functions is that there are bindings available for many other Azure techniques or Azure technologies. So for example, we can use this blob input attribute here to inject the content of a blob, of a file that is available somewhere in blob storage directly into our function. So we just specify the path to the blob container and the file. Again, we can use this placeholder, and the Azure runtime, the Azure Functions runtime takes care of downloading this blob and injecting it to our function. And we don't have to actually use the blob storage SDK ourselves to actually retrieve this blob in our function. So it makes it quite easy to integrate different Azure technologies. And yeah, in this case, we're just creating a response for the HTTP request and writing the blob content that we got injected here to the response and returned it to the client. Another key piece of technology for our architecture is going to be SignalR. SignalR is a server-to-client communication framework for web applications. So if you think about web applications, normally the communication is always triggered by the client. The client, mostly the browser, sends a request to some server, and the server responds. And that's the main way of communication. But sometimes you want to use the other direction. You want to send a notification from the server to the client. So this can be used in real-time applications like our game, or maybe you have some chat functionality. You can use it for notifications. Maybe the same, or maybe another user in your application is modifying the same content you're currently working on. If you have some collaboration software, maybe you want to update stock prices. Whenever you want to use real-time updates and don't want to use polling for repeatedly requesting data from the client, then you can use SignalR for that. The nice thing about SignalR is that it abstracts away the communication details. So there are different techniques you can use for implementing this server-to-client communication. Best case is you can use WebSockets. Nowadays it should be available in most browsers that you encounter in the wild. But some years ago, that wasn't the case, and so there were some fallback technologies. You can use long polling, for example, and there are some fallbacks, and SignalR takes care of figuring out the best way to communicate that is available in the current situation. And we don't have to care about it. We just use the SignalR API, and this whole handshake and figuring out of which way of communicating should happen is done by SignalR for us. There are two ways to use SignalR. The classic way, if you want, is that you include the library directly in your web app. So you have a browser here, and you have your web app running on one or more servers if you have multiple instances. And SignalR is tightly coupled to your web app. It's deployed to the same app running in the same process. That's the classic way. And SignalR is now also available as a hosted service in Azure. So we can use this Azure SignalR service as a standalone service and use that for the communication. So the browser is now only talking to this SignalR service, and the SignalR service is then talking to our web app. They're not running in the same process anymore. And the advantage of this mode of operation is that we don't need to keep our app running, because if you look above here, there always needs to be at least one instance running of our web application in case some user comes and wants to connect to the SignalR service. And when SignalR is running as a standalone service, then the browser can connect to the service, and this service will take care of waking up our app. And we don't need to keep an instance running all the time, which, as I said before, is good for us, because then we don't need to pay for an instance of our app running. And this enables to use SignalR with function apps as well, and not only classical web apps. So this is how we're going to implement this. Let's take a look at the code. Again, we have a C# function here. We have this function attribute applied. And this time we don't have an HTTP trigger, we have a SignalR trigger. So we want this function to be triggered by a SignalR message that was sent by the client. So this is why we use category messages here. We could also react to some connection events. For example, there's a new connection created or a connection failed. Then we could use this to react to these events as well. But in this case, we want to react to a message. This hub name isn't that important for us right now. You can think of it a bit like a controller in ASP.NET MVC. So this is a way to group functionality together. And with this syntax, we can just specify that we don't want to hard code the hub name here, but we want to read it from the configuration. But it's not that important. We're only going to have one hub in our application. And this parameter is the name of the message we want to respond to. So this function should be triggered whenever an echo request message is sent to our SignalR service. And then we can specify the name of the parameters. So these functions can also have parameters. And because of this, we can directly inject the message to our function again with this parameter here. And we can use this SignalR invocation context that we also get from the SignalR trigger to, for example, get the connection ID of the client that just invoked our function. What this function does now, as the name suggests, it just sends a response back to the client using the same content. So we return a SignalR message action. That's also a type that comes from the SignalR SDK. And we want to invoke a function on the client now. In this case, it's the echo response function, and we can pass a parameter array that we want to pass to this function that should be invoked on the client. And the connection ID property of the SignalR message action just tells SignalR to which client we want to send this message, and we just use the same connection ID of the one who invoked this function. But we could, of course, send to other connections here, and then we could implement a chat functionality or a game, like in our case. So this is, in a nutshell, how we can use SignalR in combination with Azure Functions. From the client side, we can invoke this Azure function by using our hub connection and using the invoke async method, passing the method name. So this will map to this parameter here, and one or more parameters. In this case, this will map to the message parameter. And as I just explained, this function will then invoke a function on the client as well, the echo response function. And we can specify a callback for this echo response function, specifying the argument types as a C# type arguments here, and passing in a lambda function or also a normal function that handles this incoming echo response message and do whatever we want with the message. In this case, just write it to the console. We're using C# in our client because we're using Blazor, but there are also SDKs available for JavaScript, for example. So we could also use equivalent code in JavaScript to invoke methods on the server or to specify callbacks on the client. And this is because this might look a bit weak using all these strings and untyped parameters here. But that's because we don't know if the client is actually using C#. It could be using another language. That's the reason for that. Okay, we need one more puzzle piece for our game, and that's an extension of Azure Functions named Durable Azure Functions. Because as I said before, these Azure Functions, they are for small pieces of code. And when we want to implement more complicated workflows, where we maybe want to fan out, where we want to run many sub-functions in parallel and wait until all these sub-functions executed, or we want to wait for some external event, but then it gets hard using that gets hard implementing that using Azure Functions, because there's no real good way to wait if we invoke another function. We can actively wait, for example, if we send an HTTP request and wait for the response, but then we have to pay for both functions, the one that actually does the work and the one that's just waiting for the other function to finish. And this is where durable functions come in. We can use durable functions to implement workflows. One example from the docs is this approval workflow. We have one Azure function that is triggered when an approval of some sort is requested. Maybe someone wants to go on holiday or an invoice needs to be approved, whatever. So we have one function that is triggered whenever this process starts. And then we want to send an email to a user who has the permissions to approve this. And then this can take some time. Maybe this user is on holiday and he doesn't respond within minutes, but it might take a few days or even weeks for this response. And we don't want to keep our function running, waiting for this response. We want to stop at that point and only continue once we receive the response. And if it was approved, we want to process the approval, so we want to call another function. Or maybe if some timeout happened, then we want to call another function to escalate this approval process and maybe notify someone else who has more permissions. How would it look in code? Again, we have a function with the function attribute. And in this case, we have an orchestration trigger. Because the functions we're going to use to implement workflows like that are called orchestrators, because we orchestrate the work here. We distribute the work among other functions, and here we implement the workflow. So when we want to call another function, we use this call activity async method here and specify the name of the other function. And then at that point, the orchestrator stops. It doesn't keep executing, it just stops here at this await. And only when this other function we called finished, and that might be a few seconds later, or that might be 2 weeks later, only then the Azure Functions runtime wakes up our orchestrator, and it doesn't continue where it stopped. It looks to us that way, but it actually is restarted at the top. But now, when we reach this line of code here, actually the function runtime knows that it already called this activity, and it doesn't call it again, but it just passes us the result that we have now, and we can continue. So what's happening next here is we're specifying this timeout of 72 hours. And then we wait for an external event. And again, at this point, the orchestrator just stops. And we can use some API to actually raise this event. We'll see that later. But at this point, the orchestrator stops. And again, this might take a few days until this event is actually raised, because maybe someone clicked the link in this approval email we sent them. And whenever either this external event is raised or the timeout we specified here, so 72 hours, whatever happens first, then this task finishes, and again, our orchestrator is restarted from the top. So again, we reach the first line. We know that we already called this activity. We're not going to call it again. We just reuse the result, and we run the code until down here. And now we can continue past this await here, because either we got the external event or the timeout happened, and then we can react accordingly. And yeah, that's how this orchestration workflow works. If you're interested in the details, I had a session on that 2 or 3 years ago here at Global Azure, where I talked 45 minutes only about how this works behind the scenes. You can watch the video, it's still on YouTube. If you want, I added the link to the slide here. But one important thing about these orchestrator functions is that they have some constraints. They need to be deterministic because of this replay mechanism, because we always start at the top again. So we can't use, for example, a random number generation in there, because then the function wouldn't behave the same way when it is restarted 2 days later. And we can't use the current time directly. So we can't use datetime now as we normally would, but we have to use this context current UTC datetime property here, so that it will always return the same value it returns the first time we reach this code here. But there's some pretty good tooling for this. So when we implement an orchestrator function, there are some Roslyn analyzers at work that notify us if we do something in this orchestrator that we're not supposed to do, like creating random numbers or accessing the current datetime or creating a new GUID, something like that. So that was the last puzzle piece. Now we can start putting that all together in the demo. And before I'll show you the code, I'll just restart this once so that you see the whole workflow. I only showed you the game. But when I first access my app, it just shows this create game button. When I click that, then it should start a new game. This is take a few seconds because our function app was asleep, and now it was woken up by SignalR. Now we have the game available, and we have an invitation link, and I can copy this link and paste it in another browser. So you can send it to a friend with your favorite messenger, and then using this game ID that is passed with the link, then these two browsers actually are connected in the same game, and we can start playing. Okay, and I showed you this now because this whole setting up the game and inviting other players, this is actually the workflow where we're going to spend most of the time and most of the code that we need to write. And we're going to use such an orchestrator function I just showed you to implement that. So let's switch to Visual Studio. I've got a solution prepared here. Normally, I'm a big fan of writing code during presentations so that you can see the app come to life. But yeah, we don't have that much time left. And as you've seen, this function code is also quite dense, a lot of attributes and stuff like that, where IntelliSense isn't that much help. You don't want to watch me type that, so I just prepared the solution and I'm going to walk you through the code. I've got 3 projects in my solution. I've got the Blazor project for the UI. This is just the default Blazor template. I set file, new project, Blazor app, and then I modified the code in the index page here. I've got the function app where we implement our Azure functions. And I've got a shared project because we're using Blazor, then we can use C# on the client side, and then we can reuse some models, mainly our game logic. So let's start with that. I have an enum for the player. So player can be X or O. I have a record that summarizes the parameters we need to make a move. So a move is made by a player and he wants to place his mark in a given row and column. And then we have the game class. Game has an ID and the game has the board. So this is the array of nullable players where our actual fields where we can place the marks. So it can be either X, O, or null if it's still empty. The game class knows who the current player is and if there is already a winner. It has some properties to figure out if it's over or if it's a draw. And then there's one main method in this class, try, make, move. We pass in a move and then we check if it's a valid move. So is this move made by the current player and is the board still free at the position? And if yes, then we place the mark and we check if the player who just made this move is now the winner. And then we update the current player. And yeah, the rest are just some helper methods for figuring out if a player has won. So we just check if any of the rows, the columns, or the diagonals are all owned by one player, and then he's the winner. And yeah, that's the whole code of the game class. So now let's start in the UI in our Razor page. We've got the markup code up here, CSS and some HTML, and down below we have some C# code. Here it starts. And we have some variables here for our SignalR connection to the hub and some other stuff. I'll talk about that in a second. And when the page loads, at first the uninitialized async method will be called. And the first thing we do is we create a SignalR connection to our Azure SignalR service, and we register the callbacks for the functions that we want the server to be able to invoke on our client, as we just saw in the slides before. So we create this connection here, and we specify 2 callbacks. And then we start the connection. We'll come to this part down here in a second. But as you've seen at the beginning, when you just open the page, the game ID, when we don't have a game ID yet, then we just show this create game button. So this is the whole markup that's available on the page. We have this button, and when we click it, we call the create game function. So let's take a look at that. It's quite simple. It just invokes a method in our SignalR connection called create game. This then sends a message to the Azure SignalR service, and this Azure SignalR service invokes our Azure function with the name create game. So if we switch to our functions project, then here we have this create game function that listens to exactly this create game message. And we inject another thing into our function, a durable client. And this durable client we can use to start a new orchestration. And this is what we do here. We schedule a new orchestration instance. The name of the function is orchestrator, and we pass in the connection ID of the SignalR connection that just invoked this create game function. So the ID of the client who just called this function, if you want. So what happens if we start this orchestrator function? Let's move down here. You see the orchestration trigger as before on the slide. And yeah, when the game is created, we create a new instance of our game class. We set the ID simply as the ID of this orchestration. Every orchestration that we trigger gets assigned an ID, and we simply reuse that for our game. And we get the input from the orchestration context. So this is the connection ID that we just passed in as parameter, so that we know the connection ID of the first player of player X in our case. Then we invoke an activity. We invoke another function because we want to notify the player that he joined a game. So let's take a look at this join game function, and we pass as parameters the connection ID, the game ID, and the player type. So this player, we want to notify the player that he is player X in the game with this ID. Unfortunately, when we want to invoke such an activity function, we can't pass an arbitrary number of parameters. And this is why I created this record up here, so that we can pass all these 3 values as one parameter to the join game function. So let's take a look at that. It's actually pretty simple. It just returns a SignalR message action, also as we've seen before. So we want to invoke a method on the client. The method name is gameJoined, and we pass as parameters the game ID and the player type. And we set the connection ID so that SignalR knows to who it should send this message. So we want to invoke the gameJoined method. We'll take a look at the client in a second, but let's finish the orchestrator here, because at this point we wait for an external event. We now joined the first player, but now we need to wait for the second player before we can start the game. So we wait for an external event, and the event name is player joined. So at this point, the orchestrator is going to stop. We don't use any more resources. We just wait until this external event is raised. But remember, we just triggered the game joined function on the client. So let's head back to the client. Here we specified the callback for the game joined function when we created the connection. We get passed in the game ID and the player type, and we store these in our local variables. And then we notify Blazor that the state has changed, so that the UI should be redrawn. So back up here in our markup code, again, we draw the UI, but this time game ID is not null, because we just stored the game ID in our callback. So we don't show the create game button anymore, but we enter the else case. And now we want to show this invitation link, because we are player X, we just received this message, but we still don't have a game because we're waiting for the second player. So in this case, we build the URI simply by using the URI of the current page and appending the game ID parameter as a query string. And we show that to the user. And we also show him which player he is. So this will display player X. Then we can copy this invitation link, send it to another player, and he can paste it in his browser. And because we reused the same URI, he will end up at the same page. He will again display this this UI, but now when we are in the onInitialized function, at the end, this is the code we didn't talk about before. Now we see that we have this game ID query string parameter in the URI. And when we find that, then we directly want to join this game with the given ID. So we invoke a SignalR function, then with the name join game, and we pass in the game ID. So this, again, like before, will trigger a SignalR message to the Azure SignalR service, which will then call our Azure function. So let's head back to our functions project, and we just invoked the join game method. And again, it's a very simple function. We get passed in the game ID. Again, we want to inject a durable task client. And now we don't want to start a new orchestration like we did before, but we want to raise this external event that our orchestrator is waiting for. So we raise an event, we pass in the game ID, which happens to be also the ID of the orchestration. As event name, we specify player joined, which is exactly the name of the event the orchestrator is currently waiting for. And as a payload, we pass in the connection ID of the new player who wants to join the game. So this function will activate our orchestrator again. We will start to execute our orchestrator from the top again, but this time we don't call this activity. We already did that. And this time we pass this line where we waited for the external event because we just raised this player joined event and we get the payload. So we now know the connection ID of the second player. So we pass this line, the second player joined. Now we can invoke the same join game activity like we did before, but for the second player's connection ID and with the player type O. So this will notify the other player that he has joined the game and his UI will update accordingly as well. Now we can actually start our game and we can call another activity function named sendUpdate, which will send the current game state to both players. So again, we need to build a record type because we want to pass multiple parameters to this activity. We pass in the actual game state, so our game class, and the connection IDs of our two players. So we call this sendUpdate function. And now we don't return a single SignalR message action. We return an array of SignalR message actions because we want to send two messages now. We want to send one to player X and one to player O. We want to invoke the update function on the client, and to both players, we pass in the current game state. So this will trigger a redraw of the UI. You'll see that in a minute. But first, let's continue running our orchestrator. So we invoked this sendUpdate function here. And now, again, we wait for an external event, because now we need to wait until the current player makes his next move. And we do that in a loop until the game is over. The game just started, so it certainly isn't over yet. So we just wait for an external event called move. And again, the orchestrator now stops at this position. So when we go back to our Blazor page, now the update function was invoked in both browsers. So this callback here, and we just store the game state that we just received in the variable and update the UI. And this, in case, this now leads to the entering of this if block we have here. Now we have a game, then we show the status, which is just a property I've implemented down here, which displays a string. So who is the current player, or is the game already over? Was it a draw? And did I win or did I lose? So this is what we display here. And then we draw the board where we draw the 9 diffs, which we can click on. And when I click on one of the diffs, it invokes the play function. And I guess this is not a big surprise now. What this function does, we first try to make this move in our local game instance. So you can think of that as a validation step in a line of business app where we don't want to actually invoke a server call if the validation already failed locally. So we try to make this move locally. And if it did, we immediately update the UI. And then in the background, we invoke the make move function on the backend using the SignalR connection. This again invokes an Azure function, the make move function, and this looks familiar by now. We have some parameters here. And again, we raise this event in the orchestrator, but this time it's not the player joined event like before. Now it's the move event. And as parameters, we pass in the connection ID, which player made the move, and where he wants to place his mark. And now, again, we start executing the orchestrator at the top. At this time, when we reach this line, we can pass. We figure out which player made the move. We use the same try make move function on the server to update the game. And if that worked, we again invoke the send update function that uses SignalR to update the clients, which can both redraw the UI. And yeah, that's pretty much it. That's all the code that makes up our simple tic-tac-toe game. So let's head back to the slides and do a short recap. We built a serverless multiplayer game using the following technologies. We used Blazor so that we can reuse some code from on client and server. We used SignalR in the serverless mode, so in the hosted, as a hosted Azure service in the serverless mode, so that we can use it in combination with Azure Functions. We used these Durable Azure Functions to implement our workflow, so our game logic. And if you think about it, the cool thing about this is that we never actually needed to explicitly store some state. We never wrote some game state to a kind of database or persisted that somehow. That happened implicitly because it was encoded in our orchestrator function. And yeah, even if this game goes on for 2 or 3 days, we don't need to persist the state ourselves, but this happens automatically because of the variables we use in our functions. So that's pretty cool about these durable Azure functions. And the last piece of the puzzle, we haven't seen much about that, are the static web apps. But if we just head back to Visual Studio, you can see there's a GitHub action here. And this was, most of that was generated by simply creating this static web app in Azure. And then we got this GitHub action code that will build and deploy our static web app. We just have to specify some parameters, so where our source code is located, for example. And this, where is it? Static web apps task here will figure out that this is a Blazor app and not an Angular app or a React app, and it will build it automatically and it will deploy it to Azure automatically. And yeah, what I added to this file was the another task to build and deploy our function app. And now whenever I commit some code to the GitHub repo, it will just build this and push it to Azure, and I have the new version up and running. Talking about the GitHub repo, all of the code you saw is available on GitHub. You have the link here. It also includes some infrastructure as code scripts. So if you want to get this sample running in your own Azure subscription, there's a description there, what you need to do. There are some hints for local development and how you can easily deploy this to your own Azure subscription if you want to play around a bit. If you do have some questions, then I'm looking forward to seeing you in the Q&A area at the GatherTown event. You can see the link here. I'll be there at least in the next hour. So if you have some questions or just want to talk in general about the things I just showed you, then I'm looking forward to seeing you there. Thanks for watching.